Great. Great to see such a wonderful mix of people from different fields here, as Andrew mentioned. I'm part of the Rossini project. I'm more on the human vision end of things. And I'm just going to briefly give an overview of the Southampton York Natural Scenes dataset, public dataset that James and I built with other colleagues, and mention a few bits of work that we've done using that dataset. So the scene that I'm showing here, so I'm showing one of the high dynamic range scenes from the dataset and scrolling through different exposures, because I don't have an HDR screen here, to sort of give you a sense of the huge range of luminance values that you get in natural scenes. Let's try that again. Okay, so as we all know, vision is an ill-posed problem. This is the problem that we're focusing on in the Rossini project, which is getting a 2D stimulus like this one here, and figuring out scene structure, reflectance, and the structure of the lighting. And so we know that vision is this ill-posed problem because all of these different factors go into making up the 2D stimulus. So to solve vision, to estimate all of those scene values, then we really want to have some knowledge of what the relative probabilities of different scene values are, so how probable are different surface shapes and so on, and to understand how those scene properties map onto image cues. So I'm going to focus more on this part one, and then James is going to cover some more things for part two. So what are some of the regularities of our natural world that we might learn and then kind of build into how human visual processing works? So to look at that, we've built the Southampton York Natural Scenes dataset, and that has within it indoor scenes, outdoor scenes which are more naturalistic, and outdoor scenes which are more man-made, like this beautiful view from Hampshire. And we've actually sampled 100 different scenes from a region within Hampshire around Southampton, and we've sampled scenes from all of these different 29 categories of scene types, as well as some indoor categories as well. So why did we go to all this hassle of tracking down farmers and getting into their fields and so on? Well, we really wanted to capture the diversity of scenes that humans see and sort of move around in, and that's also a central part of the Rossini project, is that we want to be able to understand what is it that makes humans, unlike most neural networks, very robust and able to function in all of these different diverse scene types. Okay, so for each scene we've sampled 3 different data types, each from a common vantage point at human eye height, and we've got 3D structure from LiDAR, so 3D point cloud, and from that we have the spherical depth map that looks a little bit like this. So here we've got colour giving distance, and then from the same point and co-registered we have the high dynamic range panoramas. So those look something like that. And then we also built our own stereo camera so that we could capture stereo pairs with a human eye offset. So here's one example of a stereo pair, and the depth map, those are also co-registered with the LiDAR. And we've got 18 of those stereo pairs for each scene, so we've captured the full 360 panorama in stereo for each scene as well. So some of the things that we can look at, and I've looked at in my lab, is what is the structure of natural lighting. We can look at how that structure of light fields really feeds into our visual processing. So we can think of any of our keep trying to use on the screen. We can think of any of our HDR panoramas as being light maps. So here's one of those spherical pictures, but flattened out to the 2D plane. And what that will tell us is that it will tell us that if we place an object in the middle of the scene, it will tell us what light is hitting that object from any direction, right? So we can think of that as a light map, and we can render virtual objects like this one within that light map. And start to understand how the structure of lighting shapes vision. So it turns out that there are quite a few things which are fairly stable over different scenes or different light maps. So one of the most simple ones is that within natural scenes, luminance tends to increase as you go up through the scene. So we've got elevation along the x-axis here, mean luminance on the y-axis, and each squiggly line is a different scene. And you can see that as you go up through the scene, things tend to get brighter. And if we take a sort of natural lighting map and then flip that so that most of the light comes from underneath, we find that messes up some of our judgment. So it messes up how we judge, say, the glossiness or shininess of objects like this one, which I've rendered in that scene. And that maps nicely on to what we know about how humans judge shape from shading. So we tend to expect light comes from overhead, and that shapes our percept of this footsteps. This is Buzz Aldrin's footstep on the moon, which most of you probably see as looking convex. And that's because when we're looking at this picture, the light is coming from underneath, but if we spin it around, and it might take a couple of blinks or a couple of seconds to flip, then you now probably see that as a normal concave footstep. But it's not only these very simple characteristics that matter to us as humans about the structure of lighting. So it isn't just like light coming from overhead, but we also use the fact that light fields have kind of higher order structure. So if we take this lighting map on the right here and gradually take away the higher order spatial frequencies from that light map, we render this stormtrooper, and it can see that as we take away that higher order structure, this actually starts to look like a matte object rather than the true glossy object that it is. So there's just a couple of ways in which we know how lighting tends to be structured, and that shapes our visual percepts. Just want to quickly mention some stuff that we've done about sort of basic 3D structure within our data set. So one of the first things that we looked at was the distribution of slant and tilt in natural scenes. And so here I'm characterizing slant and tilt in an egocentric framework, so relative to the view vector, where something which is orthogonal to the view vector is 0 slant, and tilt in the clockwise direction, so 0 tilt is ground planes, and 180 is ceilings, and 90 and 270 are going to be wall planes. So we can look, so one reason to look at that is that when we do studies with humans, we often find that humans underestimate their judgments of slant. Might be partly due to Q conflicts of how we show slanted surfaces on a 0 slant plane, but it also might be something to do with what we've learned about the structure of our natural world. So for each of our scenes, we've got our point cloud that gives us range, and then for every point within our point cloud, we've estimated what the local surface and tilt is of that point. So we can now look at how slant and tilt are distributed in natural scenes. So what I've plotted here on the right is what we would expect in a totally random world. So every surface just has a random slant and tilt. So I'm showing the log probability density in color and slant along the radial axis and tilt going around. So that's what a random world would look like. This is what natural outdoor scenes look like. So one thing you can see is this peak here. At 0 tilts, that corresponds to the fact that the ground plane sort of dominates natural scenes. And then if we look at outdoor built scenes, you'll see that peak for the 0 tilt on the ground plane is much, much stronger. But we also get this sort of band here of higher probability, which corresponds to things like vertical walls of buildings and trees and things like that. And then if we look at indoor scenes, it's once again very, very different. So the distribution that you get will vary quite a lot with the scenes that you choose to sample. Furthermore, we can actually look at the distributions of slant and tilt as a function of where you're looking in a natural scene, so whether you're looking downwards or much higher up, and you can see that distribution can also vary quite a lot. So those stats vary across different types of scene, but lucky for us, humans are spectacularly good at getting the gist of a scene, so the type of the scene that we're in, within a fraction of a second. That's something else we've looked at with our data set. In fact, there's some work that Matt's done in my lab. So I'm just going to show you a scene here. So you've got fixation cross. You're going to see a very briefly shown scene and then a mask, and then you're going to be asked what the scene type is. Okay, did you get that? Did anybody see that? Okay, road, yeah, so for those of you who didn't quite get it, it's a slower version, okay? So what was actually being shown there is Shirley High Street in Southampton, nice street scene. But it turns out that we are really spectacularly good, so within 13 milliseconds, we're able to classify a scene as being something like a beach farm or road, but we're also able to grab what the kind of coarse 3D structure is, so if it's a relatively flat scene or a structured one or closed off and so on. And one of the other nice things we found in this study is that actually having binocular depth cues helps you with those judgments. So here I'm showing binocular depth cues as motion parallax, so just flipping between the left and right eyes, and turns out that having those binocular cues actually helps you even with these very brief presentations. Okay, so that's a very whirlwind tour of the SIN's data set and some of the things we've looked at, and James will talk about some other studies. So just to conclude, human vision is tuned to the structure of natural scenes, and the natural scenes data set, like ours, can help us to understand sort of what makes humans so robust over different scene types. And now I'd just like to thank all of the floating heads who have worked with me in this. Thank you.